Okay, guys. Example 4 real quick, where we left off yesterday, part 1. We talked about in your class briefly. Write the function of degree 4 with leading coefficient of 2 that has these given zeros. So degree 4, notice how many zeros do they give me? 4 zeros. So those are going to match up. And then the other key is we can't forget leading coefficient of 2. That's the piece that is new this lesson. So a 0 of 0. How do we express that?
X.
That's going to be x.
Make it 2x and put the leading coefficient on.
Okay, hold on. I'll get there. A 0 of negative 5. How do I express that?
X plus 5.
It's x plus 5. A 0 of 4 is
X plus 8.
x minus 4. And a 0 of 8 is
That's a lot.
x minus 8. And then the leading coefficient of 2, as it was stated, you are just multiplying. And I tend to put the 2 out front. And yes, I agree. I wrote it as 2 dot x, 2 times x, but 2 times x is 2x. Okay, I definitely agree with that. From here, it did say write the function, so I am going to say f of x equals. It's multiplying it out. We have 4 pieces to multiply. So I do 2 and 2, and then those results. One of the pieces I would just do is if you think of this as 2x, how do we multiply 2x times x plus 5? Take 2x and distribute. That's probably what I would do first. So 2x times x is 2x squared plus 2x times 5 is 10x. I would put that in parentheses as one of my multiplications. And then I would multiply the x minus 4 times x minus 8. So if we FOIL this, x times x is x squared. Outsides, minus 8x. Insides, minus 4x. Minus 8x and minus 4x is minus 12x. Minus 4 times minus 8 is plus 32. Are we okay with that? And that's a binomial times a trinomial. Okay.
Oh, I didn't even do it that way. Oh,
Well, meet me in the end then. Okay, so I'm going to distribute my 2x squared.
I just did it 1 by 1. I might have messed up on that.
2x squared times x squared is
2x cubed.
2x to the fourth. 2x squared times minus 12x minus 24x to the third. 2x squared times 32. 64x squared.
Yeah. Because it's really officially like minus 4x minus 8x, but you just combine.
I went ahead and combined them in one step. Is that did I look confused?
No, I just actually put plus, like x plus 8 on my thing. So I thought it was like 4 instead of 12.
Okay.
That was just my mistake.
Okay. Okay, let's see. What am I? I'm ready to distribute my 10x now, yes? So 10x times x squared is 10x to the third. 10x times minus 12x minus 120x squared. 10x times 32 plus 320x. And then it's cleaning up like terms. I know I see 2x to the fourth. Minus 24x cubed plus 10x cubed is going to be minus 14x cubed.
And minus 56x squared.
64x squared minus 120x squared. Is that the minus?
6.
Yeah, okay. Minus 56x squared.
Yes, we got the same answer.
And then plus 320x.
I just did it like 1 by 1, 1 parenthesis by 1 parenthesis, basically.
Okay. Whereas I did 2x in a parenthesis and then 2 parentheses and then put those together.
Yeah. I just did like, I got the first parenthesis times 2x, and I took that answer times the second parenthesis, and I took that answer times the third parenthesis.
Okay. It works.
Just less numbers at a time, so I don't miss any numbers.
Okay. Obviously, there are multiple directions of ways you can handle that. As long as you do something legitimate, you're good, right? Okay. So, 2.4 part 1, that was finishing up yesterday. Long division. We had the remainder theorem and the factor theorem. Remainder theorem, you are plugging the value in to find the remainder. Factor theorem then is if you got a remainder of 0, it's a factor. If you didn't get a remainder of 0, it's not a factor. And then we had writing this function based on the zeros. Okay? Homework to go with that is 200, 1, 2, 3, 5, 13 through 24, 27, and 28. Okay, moving along to part 2. Part 2. Again, we're still talking about real zeros as a polynomial function. Here we specifically focus on synthetic division, which I'm only giving you one review just individually of synthetic division. It will come back to you. But then once we go down to examples 2, 3, 4, where we're using what's called the rational roots theorem, we'll use synthetic division within those. Okay? So, our first example. Ask us to use synthetic division to divide this cubic function by the binomial x minus 3. And write the summary statement in fraction form. Okay, so synthetic division. We start usually by putting a box. In that little box is represented by our divisor. Now, what are we dividing by? Officially, it's x minus 3. What number represents that?
X minus 3.
But we're dropping all of our variables. So basically, what I always suggested is think of it as if it's x minus 3 equals 0 and you solve that, we're going to be using 3. Okay?
Oh, goodness.
And then, next to that box, we write out the list of numbers representing our dividend. Make sure all place values are represented. So if you start with x cubed, you can have an x cubed term, x squared, x, and constant term. So, my first number here is the 2 from x cubed, negative 3 from x squared, negative 5 from x to the first, and negative 12. I'm going to leave myself room for a row of numbers, and I'm going to draw a line. Then, we start by taking our first number here and dropping it. So my first coefficient up here of 2 drops down, and that's the first piece of my answer. And then we do a multiply step.
Yeah.
So we always start with the 3. You're always multiplying by 3. In this one, it's going to be 3 times 2. 3 times 2 is 6. And that bounces up and goes under the negative 3.
Then you add it.
And then it's always add. We're going to bounce back and forth between multiply, add, multiply, add. So negative 3 plus 6 is 3. And then start over. The 3 we just wrote multiplied by the original 3. So 3 times 3?
Oh, because isn't it always supposed to get 0 at the end?
Not necessarily.
Oh,
Okay. 3 here times 3 here is 9. That's my multiply. Then we're going to add. Negative 5 plus 9 is 4. Then we're going to multiply again. So back to 3. 3 times 4 is 12. You add again. Negative 12 plus 12 is
0.
0. What does that 0 represent? That's your remainder, yes? Do you have to get a remainder of 0? No, you do not. Not all division works out. Okay? I will say in what we're doing today, as we talk about finding zeros here in a little bit, you're going to be looking for zeros. You're going to want a remainder of 0. Okay? So, a couple of things here. Yes, this 0 is my remainder. Synthetic division, it looked like you guys kind of remembered it once we got into it a little bit. Okay? And then right here, the directions asked me to write a summary statement in fraction form. And basically we're writing our answer, but a summary statement in fraction form basically says, okay, what were we dividing? We were doing this cubic divided by this, right? So the fraction is just showing your division. So the idea that 2x cubed minus 3x squared minus 5x minus 12 divided by x minus 3 is equal to what?
2x squared plus 3x plus 4.
2x squared plus 3x plus 4.
And then when you if there was a remainder, would you do it the same way as the other division? Like
You put it as a fraction.
blank. Over,
Yeah.
Would it be out of x over 3 or the other one?
The x minus 3.
It would be over the x over.
Yeah, that right there. So do remember, guys, if this started as x cubed, you're always dividing by an x to the first, yes? And so that's how we know that this one starts as 2x squared. Does that sound familiar? Okay. So the answer is your 2x squared plus 3x plus 4, but I wanted you to see if you see something written like this in an answer key or in the book or something, this is what they mean by write the summary statement. You're just summarizing the problem, that it was this divided by this and it equals this. Okay. That's a brief review of synthetic division. We're going to do more synthetic division, so that's not your only review, but that was the one to get our brains going on it, okay? Now, we're going to use this synthetic division. If you look through the rest of the problems, they all talk about finding zeros, either finding rational zeros or finding real zeros, okay? And we have something called the rational roots theorem that helps us to find all of the zeros. And what we're looking at is situations where you might not have the calculator. Okay, how do we find our zeros when we don't have the calculator? Eventually it leads to how do we find imaginary zeros. I believe that's in lesson 2.5, where we find complex zeros, and those the calculator won't find for you, so we have to have a way. Okay, so the rational roots theorem. Suppose f is a polynomial degree of 1 or larger. Then, if x equals p over q, that's going to be what we're going to use. P is an integer factor of the constant, and q is an integer factor of the leading coefficient. Okay? So, what we're looking at this polynomial. We're going to be using p over q to help us find our possible zeros. They're not all going to be zeros, but it's going to find the possible rational zeros that we can test. Okay? Notice, p is an integer factor, so it's a factor of the constant, whatever your constant is in the original problem. And q, integer factor, so it's a factor, and it's a factor of the leading coefficient of the problem. Okay? So that's what we're going to use. And that's going to help us find our possible rational roots or potential rational roots. And then we're going to work through testing them. Which ones truly are rational roots, which ones are not. Okay? So, let's go down into example 2. Okay? P over Q. Example 2 asks us to find the rational zeros of this given function. Okay? When they ask us, and specifically here, they're asking for rational. So we're not even being asked to find all real ones in this one. We just want rational. So I don't want any irrational ones. Okay? But we're going to start off by finding what I refer to as PRRs, or in other words, your potential rational roots. Okay? We're finding potential rational roots. And this is what this rational roots theorem does. In order to do this, they're going to be x values, and it's going to be p over q. Now, we go back up to how p over q were defined. P was defined to be what? Factors of the constant coefficient. In this problem, what is my constant? In f of x, what is the constant value? The 4, yes? Right here, when we talk about the constant, we're talking about the number without a variable. It's usually added or subtracted at the end, yes? So when we talk about p, p being factors of the constant, in this particular problem, it's going to be factors of 4. Okay? In the denominator, we're doing factors of q. And q is what? Factors of the leading coefficient. So I thought we did this a little bit last year.
Yeah.
Just all of a sudden dawned on me.
Yeah, we did.
What's my leading coefficient?
1.
Yes? The invisible 1 here, yes? That is my leading coefficient. Yeah, just all of a sudden dawned on me.
Okay.
Okay, so with this in mind, what are possible factors of 4?
4, 2, 1.
And when we say 4, 2, and 1, we also need to include their negatives. So I'm going to write that as plus or minus 1, plus or minus 2, and plus or minus 4. All over
Plus or minus
factors of 1. What are factors of 1?
1. Plus or minus 1.
Plus or minus 1. Now, that's just kind of my setup. That's my startup. If we actually figure out all the options, well, all my options are just putting each of these over 1, right? What's 1 over 1? 1. What's 2 over 1? 2. What's 4 over 1? 4. So what are my options? Obviously still all plus or minus, so plus or minus 1, plus or minus 2, plus or minus 4. These are what we refer to as our PRRs, your potential rational roots. Okay? Now, are all 6 of these going to be actually work as roots? When I'm talking rational roots, I'm talking solutions, I'm talking zeros. Can all 6 of these work? No, because at most, how many can there be? There can only be 3 possible. My highest power is a 3, so this problem has 3 roots, 3 zeros, 3 solutions at most. They're not all necessarily rational, so maybe not even 3. Okay. Now, how can I figure out which of these 6 work?
Plug them all in, but that would take forever.
What do you mean by plug them all in?
Like, could you plug them in for X?
Okay. So in other words, if you plug them in for X, what would you be checking? You'd be checking to see if they give you a, how do we know if they work? They what? They equal 0, right? Because if they work, if they're a factor, they give us a remainder of 0. So one option is to plug all 6 in. What's another way to check a remainder? What did we just do to start the day? Well, not to start the day, but to start part 2.
Oh, sorry, right.
To start part 2, synthetic division. Could we use synthetic division to do this? Now, okay, I let you guys fudge it a little in that. I mean, officially, what are we supposed to do? You try 1, doesn't work. You try -1, doesn't work. You try 2, doesn't work. You try -2, doesn't work. You try all 6 of them until you find something that works. Okay? I let you guys kind of take a cheat and plug it into the calculator, okay, to get yourself based on the calculator, what should I make my first guess? Does that make sense? So graph this real quick.
Right.
Okay.
Positive 2. It's the only one that's really on.
Okay.
The other ones would be, there's 3, but the other ones are like going to be decimals.
Okay, so they're not going to be rational, maybe?
Yeah.
Since my only rational options are whole numbers. Okay, and here's the deal, guys. When I say those are my PRRs, those are my potential rational roots. All of the rational roots are included in that list. Okay, it would be nice if this would cooperate. And so, hopefully, did you guys get something? And as you're looking, it looks like it crosses through 2, doesn't it? And then it also looks like it crosses through 0 point something, or negative 0 point something, and
6 point something.
6 point something. Well, that negative 0 point something and that 6 point something, are they in my PRR list? No. So what that means is those are probably going to be irrational. They are going to be irrational because I don't have any fractions here. But what we are going to do is we are going to try 2. So now, I had a graph I was going to just kind of put up here, just for a visual so you can remember what our plan was later. Okay. Just kind of the idea that my graph passed through negative 0 point something. It looks like 2. And 6 point something. And notice, did I take my calculator and find the actual 0 in the calculator? I did not. And that's not what I want you doing. You're just using it for an eyeball. And what I can say here is, based on the graph, we're going to try x equals 2. Okay? Based on the graph, we're going to try x equals 2. Now, when I say try x equals 2, you could plug it in, or what I'm going to encourage is synthetic division. Synthetic division because that will give you any other factors you might need. So, we said try x equals 2, so put 2 in your box. What goes next in my box?
1, 8, 10, 4.
Okay. 1, negative 8, 10, and 4. You know how to do synthetic division now, right? You remember? We're going to drop the 1. We're going to multiply. 2 times 1 is 2. We're going to add. Negative 8 plus 2 is negative 6. We're going to multiply. 2 times negative 6 is negative 12. I'm going to add. 10 plus negative 12 is negative 2. Multiply. 2 times negative 2 is negative 4. Add. 4 plus negative 4 is 0. What's that tell me?
And it's 0.
Okay. The 0 worked. The 0 says it worked. I got a remainder of 0, so that means that this 2 is a factor. Now, the reason we like to use synthetic division is that we know 2 is a factor, and so we'll put that in a factor form here in the moment. In fact, I think I'll go ahead and do it. So if we're taking f of x here, basically we're factoring it. 2. What does a 0 of 2 represent as a factor? That is the factor x minus 2, right? So we know that's part of the factored form. Now, we divided by x minus 2. We got a remainder of 0. What's our other factor?
Yeah, those.
And say put the variables back in. 1, -6, -2 represents 1x squared minus 6x minus 2. That's my other factor. X squared minus 6x minus 2. Okay? Now, our question on this particular problem was to find all rational zeros. Rational means I only want zeros that can be expressed as a fraction. We know from this, we already found a 0 of 2, yes? X squared minus 6x minus 2. Is that going to factor? No, it's not going to factor. And folks, if it's not going to factor, we'd have to use quadratic formula. Okay? It's going to give us square roots that we can't do. It's going to give us big, long, messy decimals. Are big, long, messy decimals rational? No. So this right here, if they ask us for all real roots, then we keep going and we find these solutions. But it only, in this case, wanted what? Rational zeros. So my only answer is 2. Because this right here, I'm going to write it down so we have it, does not factor. Thus, irrational roots. So my only answer is x equals 2 on this one.
So the factors, you just set them equal to 0?
Yeah. Okay. Questions here?
Great. Example 4 looks
Okay. Do we have what we need here? Because I'm going to change screens and go to my example 3. And realize, what's that saying about these two right here? Those two pieces are my irrational roots. They would be the answer to this piece if we put it in the quadratic formula and solved it. But they only wanted rational zeros, so we get to put there. If it said all real zeros, I would keep going. Okay, example 3. Let's try this again. Notice it says to find all rational zeros. So we're going to start this just like we did example 2, which means we're going to start by finding our PRRs. Okay. PRRs. Remember, this is where you do, officially it reads as P over Q. P represents factors of what? Factors of the constant. So factors of -2. Q on bottom represents factors of what? The lead coefficient, which is 3. Okay. Well, it says -2, but since we use plus or minus, it doesn't really matter. What's factors of -2? 1 and 2, right? 1 times 2 is the only way you can get 2. So plus or minus 1, plus or minus 2. What are factors of 3? Plus or minus 1, plus or minus 3. Okay. I want to go through. Don't leave your answers like this for if I'm asking you specifically for your PRRs. Don't leave them like this. Go through and make a list of the specific PRRs. So I would start off by putting everything over 1. So what's 1 over 1? Plus or minus 1. What's 2 over 1? Plus or minus 2. And then I would put everything over 3. So 1 over 3, plus or minus 1/3, and 2 over 3, plus or minus 2/3. What is this list I just found? Those are your PRRs, potential rational roots. Again, we're asked to find our rational zeros. We've got 8 choices. At most, only 3 can work. Okay? So, what do I see you guys already doing? Put it in the calculator. And again, remember, I'm not asking, don't find the zeros on the calculator. That's not at all what I want. You're just using it as a starting point there. Now, I'm going to do the same thing I did last time. And I'm going to sketch us a graph just to have in our notes. What's it look like your graph is possibly doing?
There's 3 of the PRs.
Negates 3 of the PRs?
Unfortunately.
Okay. What are the obvious 2?
-2, +1.
-2 and +1, just by eyeballing it. Again, we could be wrong. Maybe one of those is just off slightly. Maybe it's not actually. But -2 and +1. Could that other one be a possible PRR?
-1/3.
It looks like it could be -1/3. And here's what I'm going to tell you guys. If you have leftovers that aren't in my PRR list, they're going to occur in pairs. Because irrational roots only occur in pairs. Okay? So that fraction one, it has to match with another irrational if it's irrational. So it very possibly is one of our fractions here. So.
Wait, so therefore, we don't have to do any of the division, right? Because we have 3. That's the max you can have.
We're going to check it. We're going to check them because we don't always know this. Okay, so maybe a 1, maybe a -2, and then the one I would say for the last is maybe a -1/3. Okay, so I'm going to say, again, I'm just writing this down so you have it in your list. Based on the graph, I'm going to try x equals -2, +1, and -1/3. Okay, and again, I'm letting you off the hook a little bit because I could say, no, you don't get the calculator. You just have to try something until you find something that works, which is annoying, but that is the official option. Okay, pick one that you're pretty confident of. So I would say pick the whole number, right? Now, stay with me. Don't get too far ahead of me on this checking stuff. okay? Because I want to do something here. So -2. What's going next to my -2? 3, 4, -5, and -2. Yes? Do your synthetic division. Drop the 3. -2 times 3 is -6. Add 4 and -6 is -2. Multiply. -2 times -2 is 4. Add. -5 plus 4 is -1. -2 times -1 is +2. -2 plus 2 is 0. What's that 0 tell me? It works, yes? Now, pause before you go on to the next one. We know -2 works. What am I going to suggest from here? To try 1. But here's the catch. What's going to make your life the easiest? Don't go back and use your original list of numbers. Don't go back and use the original problem. We're factoring this down. We just divided by -2, or the factor x plus 2. What's my result? That 3, -2, -1. So now when you do your next synthetic division, don't go back and use the original problem. Use this new factor. So bring up, because what it's doing, it's allowing us to factor it now. We're going to use the 3, -2, -1. Are you with me there? That's why I said don't get too far along. Drop your 3. 3 times 1 is 3. -2 plus 3 is 1. 1 times 1 is 1. -1 plus 1 is 0. Did it work? Yes. Now, you can check the last one, but I'm also going to argue we don't have to check the last one. I'm going to show that I have proof that I know it works. Okay, what does this 3 and 1 represent? Original problem was 3x cubed, yes? So what's that mean this 3 right here is? That was 3x squared. Carry it over here, this is 3x squared. What's this 3 represent? 3x. So think about this as 3x plus 1. That's our final factor. Can you just set that equal to 0 and solve? And show what our third factor is? 3x plus 1 equals 0. 3x equals -1. What do we get? -1/3. So, between all those pieces, what did we just confirm? My zeros are, my rational zeros are -2, 1, and -1/3. Okay.
Here's the last one. Instead of going like quadratic formula, you might as well just set them all equal to 0. Like if you don't want to do quadratic formula, you can just set all the possible rational roots equal to 0. Or we plug in the equation.
But, well, okay, so example 4. I'm obviously not getting through example 4 today, so I'll explain my plan here in a moment. Example 4, what's the difference though? It says what?
Real.
All real zeros. What's going to happen if I just tell you up front, yes, some of the zeros are going to be rational, because there's going to be how many zeros? It's going to be 4. Some of them are going to be rational, but there's going to be some that are irrational, which is going to involve quadratic formula, or there's actually another solving step we can use for this one, okay? So here's what my updated plan is. Okay, Monday, I will go through example 4 in the notes. And then after lesson 2.4, we are quizzing next week on Wednesday, is what I just made lesson plans for. Okay, so my plan was review Monday, Tuesday, quiz Wednesday. We're still gonna stick with that, but Monday we'll finish this last example. So what I'm gonna give you, what I'm gonna say, part 1 homework, I want that due Monday, we will check that Monday. Part 2 homework, I'm gonna leave that and we'll check that Tuesday. Because you can work somewhat on part 2 homework, but we need to talk about how to deal with all the real zeros. Okay? So we'll check part 1 Monday. I'm still gonna hand you the review worksheet on Monday, and I'll teach this last example. We'll check part 2 on Tuesday. You have that review worksheet still to be working on, so you don't wanna save all of this homework, right? Quiz on Wednesday. I think that'll work. I'll revise it on Monday if I have to, but I think that's what I'm going for, okay?